Do. Well, I don't know. He's the one that put Fauci into place. So there you go. I will begin with a word of prayer. Well, I was answering a question which wasn't asked on audio, so it's safe. I don't have to edit anything. So it's been recording. So I'll begin. Dearly Father, we thank you for this day, and thank you for these students in this class. Help us to glorify you, what we do. In your name I pray, Lord Jesus. Amen. All right, let me begin with a simple but kind of calculation. So, remark. For t linear transformation from v to w, if we calculate this, meaning the quotient by the kernel, right? Then that is equal to what's it equal to? Well, it is equal to x and v, such that what? My bad. It's equal to, I've already messed it up. X naught plus x, such that t of x is equal to 0, right? Notice t of x naught plus x is equal to 0. Well, not equal to 0, but is equal to what? T of x naught. Thus, x naught plus x is an element of the inverse image of the set containing t of x naught. Therefore, x naught plus kernel of t is equal to the inverse image of t of x naught. As I was claiming, the fiber of a linear transformation is in fact a coset of the kernel. This is the calculation which vexed me last time. If you'd like to see it made more complicated, I have a double containment proof on the piece of paper up here if you really want to look at it, but this is it. Now, of course, if t of x naught is 0, then, special case, right? Kernel t we can also write as a fiber, right? The kernel t is literally the inverse image of 0, right? The kernel is a fiber of the map. It's everything that maps to 0. So that's one thing, because I got stuck on that last time I could try to find a reason, but I guess the short answer is, women. It all goes back to Eve. We live in a fallen world, Oh, I'm sorry. You guys are complementarians. You share the blame? No? Yeah? All right. Do I need to say that's a joke? I guess I need to say that was a joke. There you go. Is that better? No, I shouldn't be fired. Okay, very good. So we looked at the quotient space right last time. We proved the dimension theorem, and I stated the first isomorphism theorem. but I glossed over something which requires a definition, and we should make that definition now and study this map a bit. So definition, the quotient map. The quotient map for v by w is pi, which is a mapping from the quotient space of v by w. I'm an idiot. So from v to v by w, there we go, that's better. Watch out, because I'll do stupid stuff today. I warned you guys already. And the definition is simply this: pi of x is equal to x plus w, right? Or if you like, in our other notation, this, right? Again, this is a dangerous notation because you lose track of which subspace you're forming the quotient by. So the first theorem to prove about that, so we'll start out real easy today, which is this theorem. Pi is a linear transformation from v to the quotient. So let's check that out. So here we go. We got pi of cx plus y is cx, cx plus y plus w, all right? I'll use the coset notation to make the proof look harder. If I use the bracket notation, it would make it look too easy. I don't want to give you guys this false sense of security, so I'll try to keep you confused. So this is c times x plus w plus y plus w by the definition of addition on the quotient vector space, but that is nothing more than c times pi of x plus pi of y. So there you go. The the quotient map is linear. What's its kernel, by the way? Is w, right? Kernel of pi would be equal to x and v, right? Such that pi of x is equal to 0, but that's equal to 0 plus w, right? So that's literally w. Right. I guess I'm not, sorry, one more thing here. So this amounts to the equation x plus w equals to w, right? Or 0 plus w. And the only way that's true is if x is in w, by the theorems we proved like time before last, actually. All right. So yeah, the kernel of pi is w. All right, so moving along here. Oh, sneeze coming on. Must suppress. Ah, ha, take that, sneeze. I stopped it. So here's our theorem. The first isomorphism theorem of linear algebra. And you might wonder, why is it called the first isomorphism theorem? Any ideas?
Because there's more?
Because there's more, that's right. There is also a second, a third, and indeed a fourth isomorphism theorem, commonly known as the lattice isomorphism theorem. And my brother claimed that like pretty much everything could be proved with the lattice isomorphism theorem, but it's like, it just crushes everything in its path. But it's sufficiently technical that I don't think it's a good idea to invest all of your energy and understanding. I don't know, I have mixed feelings. Anyway, so first we'll do for us for now. But yes, there is a second and a third. So here's the theorem. If t from v to u is linear transformation and w equal to the kernel of t has quotient map pi, then, so that means what? That means that pi of x equals to what? X plus w, right? That's what that means. Then t bar as a mapping from the quotient space of v by w to u, defined implicitly by t bar composed with pi equals to t, is an injection all right. In particular, t bar of x plus kernel t is equal to t of x for each x plus kernel t in v by w. Now you might be wondering what's the difference between the upper and lowercase kernels in here, and the answer is how I typed it. So moreover, in other words, it's not significant. Moreover, v mod the kernel of t is isomorphic to the image, which we could call t of v. All right. So there's a little bit to prove in here, and let's just take it in little doses, all right? So maybe you've not seen something defined implicitly before like this. It's kind of annoying to have a definition like that, but we'll see that it works. We're going to be able to use that implicit definition to affirm all of the truths that are claimed here. So let's start with the claim that, so first of all, we need to show that t bar is like single valued, right? And there's something to show because notice that the input is a coset, right? So, sometimes we get into trouble with those. All right, so here we go. Actually, I actually start with showing it's n2. My bad. Notice, I'll do it up. Well, rats. Fine. Phooey. Yes, I've spread on the board now. Let's see here. T of x is an element of u for each x in v, hence t bar is into u. Let's see if we can understand my sentence. What am I saying? So we have this data and we're trying to prove assertions about this t bar map, right? The first one is that it actually has a codomain as labeled. Does it? Well, if t bar is defined by t composed with pi equals to t, then since t of x is in u, if I look at, if I plug in oh, it's fine. I'm sorry. Oh, my bad. So I plug in x into here. I get pi of x. Pi of x is x plus w. But then that's supposed to be equal to t of x. Well, t of x is in u, so the output is appropriate. Like I said, I'm going to say stupid stuff today, so let's go on here before I say something stupider. Is it single valued? Single valued. All right. In other words, if we have, so t bar is a mapping from the quotient space, so let's suppose x plus w is equal to y plus w, right? Then we have t bar oh man. So then, well, let me get to the point here. Then t of x is equal to, oh man. Just a second. Let me change colors. That will help. All right. Okay, so this means that x minus y, by our work the other day, is an element of the kernel, right? W is defined to be the kernel here. So we know that t of x minus y is equal to 0, right? But what does that mean? Well, that tells us that t of x minus t of y is equal to 0, right? Thus, t of x is equal to t of y. I'll switch colors again, that will help. Thus, t bar of x plus, yeah, okay, so t bar of x plus the kernel of t, by assumption that's equal to t of x, right? But that's equal to t of y, but that's equal to t bar of y plus kernel t. Therefore, t bar is single valued, right? So if I take two different representatives of a given coset, we get the same value. So it's single valued. There's always a question whenever you define something using cosets, whether or not, you actually have a single output. So I'm just checking on that. Are we good? So next we'll show that it's a linear transformation. This will go easier. Is t bar linear? All right, so let's look at t bar of c times x plus w plus y plus w. All right. So that is equal to t bar of cx plus y plus w, right? By definition of addition in the quotient space, right? So then what? Then by definition, by the implicit definition, this is then equal to, so you've got t bar composed with pi of cx plus y, right? But by definition, t bar composed with pi is t, right? So this is equal to t of cx plus y, which is ct of x plus t of y, which is c times t bar composed with pi of x plus t bar composed with pi of y, which is c times t bar of x plus w plus t bar of y plus w, which is linearity of t bar. I did the details a little bit different than in the notes. Like sometimes when I'm thinking through it, I don't think of writing this step down, but I think maybe it's helpful because it just goes directly back to like this. But I guess the question is, I mean, logically speaking, guys, the question is whether, all right, let me understand that this equation right here and this equation right here, they're the same equation. The one is in terms of maps, the other is in terms of how the maps act, but it's the same statement, really. I mean, they are different statements, but, you know, it's like f versus f of x, you know? It's that kind of difference. But when we feed x into pi, it's x plus kernel. So t bar composed with pi of x is this, and it's supposed to be equal. So that's like, so in my notes, I'm logically operating with this in the proof I have written, but what I wrote on the board, I was, you know, forcing myself to rewrite it as the composition of t bar and pi. Okay, I'm not saying anything terribly interesting, so let me go on. So how about injectivity? So suppose we have x plus w and y plus w in the quotient of v by w, and we have you know, t bar of x plus w equals to t bar of y plus w, right? Uh-oh. Man. I got more sneezes. I think I made it. All right, so what's next? So this gives us what? This gives us t of x equal to t of y, right? Which gives us what? T of x minus y equals to 0 using linearity of t, which tells me what? X minus y is an element of this subspace which we're forming the quotient by, kernel t. Which, again, going back to the class before last, implies that x plus, you know, w is equal to y plus w. Therefore, t bar is injective. And the rest of the theorem just follows from what? What was the rest of the theorem? Right, so can you see why that would be true at this point? We have the t bar is an injection, right? T bar is an injection from here to here, right? So if we go back to last class and do what Gideon told us, which was to swap out the domain for the range, then that elevates t bar to an isomorphism. Because it's one-to-one, and it becomes onto if we just swap out u for the image of t. And that's it. That's the first isomorphism theorem. So, any questions? Yes, no, maybe so. Let's see if I've got another example. I'll do the example I have here. Oh, no. Well, I mean, I have a few, I hope, interesting examples in your homework for you guys to mull over. I don't think they're particularly difficult or anything. I guess this is example 1. So if we look at t of VW equals to v. And so here T is a mapping, linear mapping from V cross W into V, right? My claim, and you guys see if you think it's reasonable or not. How about you guys tell me? What can you tell me about this map, T? I'm working too hard. You guys tell me what it is. What can you tell me about it? What's its properties? It's definitely not, yeah, it's far from injective. Very good. I'll buy that.
Surjective.
It is certainly surjective, right? Very good. Is it linear? It's pretty clearly linear. If you put in cx, plus y into the input, you'd get, the output. Like, it doesn't matter what. It is linear. You can prove it. And so the kernel here, what is it? Right? Which, if we want to write that sort of like set theoretically, I'll take it. You got yourself what? 0 Cartesian product W, right? That's the kernel here. And you told me that, the image of T, or the range, if you like, is all of V, right? So what does the first isomorphism theorem tell me here? Simply this, that if we take V cross W as a Cartesian product, the direct product space, and we quotient by 0 Cartesian product W, which is the kernel, that is isomorphic to V. What do you guys think? I think it's kind of funny, right? It's like the W's cancel. And then V over 0 is just V. Oh, wait, what? No, whatever. Yeah, don't go too far. Don't go too far. Here's another one. How about the identity map from any vector space to itself, right? That's obviously a linear transformation. What happens when you apply the first isomorphism theorem to this? The kernel of the identity is just the set containing 0. Right? Here I'm talking about, of course, it x equals to x for all x in V. Yeah? The identity map. And it's also pretty obviously a surjection, right? So what does the first isomorphism theorem say here? It says if we take V and quotient by the kernel, which is 0, it's isomorphic to V. So again, calling this division by 0 is not quite accurate. If we used a notation that was more like this or something, it might, but then I use that for set difference, so we can't do that. And the quotient notation is pretty standard for vector spaces. Although maybe it's worth taking just a second of our time to talk about what this is. It's kind of funny. So what you're looking at, right, is you're talking about x plus V, right? Well, excuse me, x plus the subspace 0, right? Such that x is in V. Or if you like, you're looking at, I'm not talking about V. This is V by 0, my bad. Or in other words, it's the set of representatives x such that what? I can describe it over here. X equals to y if and only if what? X equals y, right. It's pretty dumb. In other words, what this is it's the set of singletons. It's quite obnoxious. All this thing is like taking every vector and replacing it with the set that contains that vector, but then doing everything else the same. It's just always like putting curly brackets around all vectors, technically speaking. It's very dumb, but that's what it is. And so it's not surprising that this is isomorphic to V, right? It's just a dumb notation for V. Yeah.
And what you started with is isomorphic.
Oh, this?
At the top of the table. Identity.
Oh, yeah, this is an isomorphism. The identity map is an isomorphism.
So it makes sense if you were adjusting it to be isomorphic, you wouldn't really be doing anything.
Right. I mean, I say not doing anything, but it's not entirely accurate, right? I mean, we are doing something. I mean, it is. They are different point sets. It is true. Oh man, did I? Oh well, that was dumb. All right, well I'm gonna have to go off memory, which seems like a perilous proposition today. But let's see here. Well, I'll start here. There's one other interesting example, I think, involving like even odd functions. So you can look at function space, and you can look at the subspace of even functions or the subspace of odd functions. If we're talking about functions with a real domain, you know? So that's kind of an interesting example. But I think I should go on here for the moment. So our next topic is independent. Well, there's two topics really, okay? So the one is independent and invariant subspaces. So independent has nothing to do with a linear transformation, all right? So independent subspaces, so here, like for example, if we have W1 and W2 are subspaces of a vector space V, all right? And W1 plus W2, which by the way is defined to be x1 plus x2, such that x1 is in W1 and x2 is in W2. All right, so it's the set of all sums of vectors from W1 and W2 respective. So like your first homework problem that you, of course, have already by now done is to prove that the sum of k subspaces defined in this way, in fact, forms a subspace. It's just a subspace test theorem. It's like very easy to prove. One way you could do it is you could prove it for two things, and then you could use induction to prove it for k things if you wanted. That would be one way you could do that. I don't think I have an induction in my solution probably, but anyway, my point to you is that this is a new subspace of V. In our current context, I want to say it's equal to V, all right? So in other words, the subspaces W1 and W2, you could say that they generate V. Their sum generates all of V, right? And in addition, we have W1 intersect W2 is the set containing 0, and that's it. If that's the situation, then W1 and W2 are independent subspaces. So that's a definition we could give, yep.
If we say that W1 intersection W2 is equal to 0 set, then can we say that W1 union W2 would generate V as well? Or am I miss?
Probably. The union of W1 and W2 is a subset of W1 plus W2 because, of course, you can take the particular case that you've got x1 or x2 is 0. So it is somewhat obvious that the union of W1 and W2 is a subset of this. Is it a generating set? Yeah, I think so. In the case that their sum is V.
Yeah.
Yeah. So that's what we mean by independent, two independent subspaces, all right? Now, invariant subspaces, that's a slightly different conversation, which I won't continue much today, but here we're talking about T, a linear transformation from a vector space to a vector space, which makes T is what's called an endomorphism. An endomorphism is simply fancy speak for a linear transformation from a vector space to itself. And in this context, if W is a subspace of V and T of W is a subset of W, then W is a T invariant subspace of V. So invariant subspaces of a given linear transformation are very important, and we'd like to understand those deeply. But these two topics kind of go together, right? So my goal is to kind of explain both of them, but I'm going to focus mostly on independent subspaces for the remainder of class today, all right? So this is how it goes for 2. How do you think the definition of independent subspaces looks like for 3? What would it take for 3 subspaces to be independent? Like what if I have W1, W2, W3 subspaces of V, and I want to define those being independent? We need what?
W1 plus W2 plus W3 equals V, and the intersection of all three of them is so contains 0.
And okay, so the intersection of all three is 0. That was the answer I was hoping for. So cool. Now, one of the things we'd like for independent subspaces to behave, we'd like this to be true. We'd like for the dimension of, say, W1 plus the dimension of W2 plus the dimension of W3 to be equal to the dimension of V, right? That is something that should be true for these independent subspaces, all right? And it is true for the properly defined case of 2 independent subspaces up here. But let's find out if this plays nice with that concept. Let me show you an example. What example am I on? 3? All right. How about this? So here's your W1, here's your W2, and here's your W3. Let me show you a super slick notation for span. You can write W1 as E1R. This is E2R. This is E1 plus E2R, assuming that this is y equals x. That's just a quick notation for a vector, a span of one vector, just vector times reals. Okay? What's the intersection? See, it's 0. But what's this dimension of W1 and 2 and 3? They're all one-dimensional. So the sum of their dimensions is 3. But this is the plane, right? So 3 doesn't equal 2. It doesn't work. But this is the answer I was hoping for. Because this is what everyone thinks. To start with, everyone wants to say this. Like, I thought this also. But this doesn't work. This is not what is meant by independent subspaces. What we need, instead of this, is we need that W1 plus W2 intersect with W3 is 0. And we need that W1 plus W3 intersect with W2 is 0. And we need that W2 plus W3 intersect with W1 is equal to 0. We need all three of these conditions to affirm the independence of these three subspaces. This is related to the problem of counting things in multiple intersections, but I don't have that right in front of me right now. I can't make good on that comment here. I'm not well enough to finish that thought. But there's something to say here about the principal exclusion and inclusion. Anyway, so yeah, that's what we mean by independence of three subspaces. Now, I want to show you guys a theorem, a big theorem, that it took me, I don't know, day and a half to type up. But, and it would take me a whole class period to prove all this, for sure. But what I have here is a list of, I think 4 or 5 equivalent characterizations of independent subspaces. All right? So let's look at this together here. And then I'll think about my, oh man, I'm stuck in the, physics gets me into something, but they can't get me out. I'm just going to have to shut down Chrome. All right, Chrome, you're dead. Come on. Task. End task, yes. Haha. There we go. Oh, where'd you go? There we are. This right here. Now, I originally was teaching this class with, I don't know when it was, maybe, I think it was 2017, something like this. And I had notes written up for 4 of these conditions, right? And I'm just minding my business, trying to teach my class. And then I have a student in the middle of class go, "Professor, I think there's another criteria you could put here that would be equivalent to the 4 you already have." And I'm like, "What?" And he's like, "Yes, it's that 0 has a unique representation." So this was given to me during class by one of you guys. His name is King. So I talk about King from time to time. He's an unusual student. So here's the 3 characterizations. The one I'm just explained to you for 3 things. It says that if you add together all of the spaces but one and then intersect with the remaining one, it has to be 0. That has to be possible for all possible subsums of your, K subspaces. So there's just one thing to check for 2. But for 3, you got 3 things. And for 4, you've got, it's not 4 things, it's more. All right. Anyway. Well, maybe it's still 4. Yeah, it's still 4. What am I talking about? It's just 4. All right, great. I'm a dummy. Maybe that was, no, I guess it's still, all right, I'm going to shut up. So that's, I take that as the definition, I think. Actually, to be fussy, I may have forgot to make one of these the definition, but oftentimes number 2 is taken as a definition. Since these are logically equivalent, we could make any one of these the definition of independent subspaces, all right? So another one is that, and sorry, I'm using pi again, but it's going to happen. This is the week of pi for you. We had the pi as a product, then we got the quotient map pi, and now we've got another pi. It's just pi, pi, pi all around. But none of them is the ratio of the circumference to the diameter. I'm so sorry. So anyway, so the mapping defined from the Cartesian product of the K subspaces to the vector space, defined simply by adding the inputs, ka-chunk, 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 just addition, that's all it is an isomorphism. That is one way you could characterize independence of the subspaces. What that means is that for the subspaces to be independent, the space itself is isomorphic to the Cartesian product of the subspaces. 2 we talked about. 3, So here, I'm using this notation. And by the way, when any of, and so here's the other thing, is when any of these five conditions are met, we express that by saying V is equal to the so-called direct sum, the internal direct sum of W1 through WK. So this notation indicates, and I used it over there, you noticed, that plus with a circle, that's independent. That expresses independence of W1 and W2. So the other way you could say, but here's really kind of more the point here, is every vector x in V, there is a unique choice of x1, x2, da da da, xk, such that x is the sum of x1 through xk. There's a unique breakdown of the vector into vector components in each one of the independent. Probably. I didn't have an adapter today. Come on. Well, that's fun. There we go. So there's a unique vector component in each of the subspaces whose unique, that unique vector component added together all the way across gives you the vector back again. It turns out, though, that in fact, if you just know that's true for 0, if there's only one way to get a sum of vectors from each of your k subspaces equal to 0, like that has to be that all of these are separately 0. That alone gives you independence of the subspaces. And, oh, I'm sorry, the backdrop to all of these is the presupposition that the sum of the subspaces is in fact V. I have to assume that generating, that's the backdrop for all of this equivalence. And again, your first homework problem is to prove that the sum of W1 through WK is a subspace of V. It's just when it's equal to V, this is most interesting. And then number 4 is oftentimes useful if we have a basis beta I for each subspace Wi, right? If the union of those is a basis for V, that also gives me independence of the subspaces. And it's perhaps instructive to look at my example 3 and see how each one of these criteria fails for these 3 subspaces, right? Like the basis for W2, W3, and W1 in my example were like E2, E1 plus E2, and E1, right? You union those, you've got 3 vectors. That's not a basis for R2 because it's linearly dependent, right? So that's how that fails. And if you look at the sum, if you look at the vector sum of any 2 of my subspaces, it's the whole plane. So the intersection with the remaining subspace is that whole subspace, not 0. So it fails, right? Anyway, so yeah. So the proof of this equivalence, it is a lengthy proof. We'll just do a teeny bit at the moment. And the logic is this. To prove the equivalence of 5 things, the easiest way to do it is prove 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and then 5 implies 1. See, then you've also got all of the other implications if you run through it. So this is a kind of circular logic which is legitimate, right? Maybe it's elliptical logic, that's why it's okay. But anyway, so I start by presupposing that that is an isomorphism, all right? And then I suppose I have x in the intersection of wj with all these, which means that we have x in wj and x is in the sum of all the spaces except for j. And so that means that there exists x sub I and wi for I not equal to j, for which this is equal to all that. Which then, if I rewrite that, I have x1 plus da 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 dot plus xk equals to 0. But since it's an isomorphism, we know that the inverse to a linear bijection is itself a linear bijection. So I can take the inverse, and it's easy enough to write the formula down for the inverse of pi, right? The inverse of pi, it takes the sum and spits out the tuple, right? So that maps to this, and that's equal to 0, which proves that x has to be 0. But x was an arbitrary point in the intersection, so we've proved that the intersection of wj and the sum of the rest of them is 0. So 1 implies 2. And so it goes. But anyway, what's going to be much more interesting than this proof, and I'm not sure, I will do more of it next time, but what actually becomes much more interesting is the question of what happens for us when we have a linear transformation and we have not one invariant subspace, but suppose you have k invariant subspaces, right? And suppose they're all independent. What happens to, the story of the matrix of the transformation? What's that look like? What does that reveal for us? And we're going to find out that that's actually quite interesting. So anyway, that's where we're going. But I think I'm out of time for today. So I will shut up.